How to off this light? Oh yo. Nice. How to just off the front light? Oh yo. Okay. All right. So are we recording? Okay. Okay. So hi everybody. My name is Tawaku. Okay. All right. And today, right, I'll be talking about our universe. I'll explain more on the term later on. Okay. But before we start, right, I just wanna check in on everybody. How's everyone doing? It's like week 10 already. How's everyone doing? Everyone doing fine? Doing good? No? Okay, can. Okay. So right. So I'll talk about time later on. So welcome to NUSAS, right? Some of you are first time here, some of you have been here for quite some time. As the name suggests, okay, NUSAS is an astronomical society. So astronomical society is a place where like-minded individuals like yourself come together to to think about astronomy, right? So every week we look at celestial bodies and planets, and we sort of gasp at their majesty, at their greatness. But today, right, I'll be deviating slightly away from the topic of astronomy, but I'll be looking into asking the question, what are we seeing? Okay, now you might be thinking like, what kind of question is that? That's quite a dumb question, right? To ask, what are we seeing? I know, we're all looking at space, we're all looking at planets, but I want to ask you all, what does it mean to see what we are seeing? What do these objects represent, right? So today, right, I want you to think about these questions, okay? No prior knowledge in astronomy is needed. I just need you to follow along and enjoy the show, all right? For I am a mere observer to the symphony that is the universe. Oh yo. Okay, so all right, this will be the agenda for today. Okay, so I'll be looking at the convergences of astronomy and philosophy. Okay, so it's going to be very, very interesting, very abstract. Just follow along on this journey as I go deeper and deeper into a lot of thought-provoking questions, right? So I'll be talking about things like parallel universes, what is gravity, what happens if you travel at the speed of light, and then I'll be going deeper and asking what is time, and even how to build a clock, okay? And then I'm going to be questioning science. What is science? Is there a scientific inquiry? And then I will try my best to link all of this with you. Okay? So, this is where we are today, right? This is Earth. And Earth is in here, the solar system. And the solar system is in here, the Milky Way. And we are in here, right? This is some galaxy. And our galaxy is in here. What is this? This is this is what we call the observable universe, right? I'm sure all of you would have heard the term before. This is the region of space that can be observed from Earth at any present time. This is the region where light has had enough time to travel to us. But beyond this, there exists a realm that is so mysterious yet attracting. Okay? So we've all heard that the universe is expanding. But do you know what it is expanding into? Anybody has any idea? What is the universe expanding into? Truth be told, we don't know. We really don't know. It seems to be the case, okay, that space and time originated from the Big Bang. So talking about what's outside of the universe is like asking what's north of the North Pole. Doesn't make sense, right? Our concepts of outside probably only apply within this universe, within our observable universe. So we honestly don't know what the universe is expanding into. Okay, we just don't know. But this is the fun part, right? Isn't it kind of fun that there's still a bit of guessing, there's still a lot of work that needs to be done. Okay? So moving on, right, when we look far beyond the observable universe, and if you accept that the universe spans to infinity, then we come across this very interesting concept called parallel universes. Okay? Parallel universes in quantum physics, right, might actually be real. It might actually be possible. Okay? So obviously this concept pops a lot in a lot of sci-fi and action films, but there's some very, very good arguments to how this concept might actually be real. Okay, there might be some evidence to suggest that this is real. So that's the name parallel universes has a lot of different sort of names, right? It's called the many worlds interpretation, maybe called the relative state formulation, the multiverse theory. But the interpretation that I'll be looking at is called the Everettian interpretation. Okay. This interpretation basically is invented by this guy called Hugh Everett, okay, back in 1957. And as part of his PhD, he put forward the theory of the universal wave function. Have you all aware of the wave function in quantum physics, which basically states the probability of a certain quantum function to occur? That's just all it means, right? Okay. So he put forward this theory. Now, this theory sounds pretty cool, okay, because at its crux, his theory states that all possible quantum measurement outcomes are all equally real. What do I mean by that? So let's break down what that means, okay? Unlike almost every other theory of physics, which is deterministic, what does it mean to be deterministic? It means that if you know all the information about a specific system, you can tell exactly what will happen in that system. But quantum physics is not deterministic. It is probabilistic, right? Which means that for a given setup, for a given experiment, it can only tell you what is likely to happen, what might happen. It will not tell you what will happen, right? It can only give you a set of probabilities, and then you use that probabilities to judge what might happen. So it somehow turns out that at the most fundamental level, the universe works on a lot of probabilities. So this is just an inherent element of randomness, and it exists at the base of our reality. But this guy's idea was this, that he says that all probabilities already exist. Okay? When we observe one of these two outcomes, we are just living on one of the timelines. But that's not to say that the other timelines don't exist. Okay? It's not that the other ones never happened. It did happen. We just don't live on it. Okay? When we do experiment with possible outcomes, right, what happens is this wave function essentially will collapse and form straight lines. So, example, y equals to a straight line, right? Just a horizontal straight line. Okay? But this doesn't just apply to human experiments. It applies to every single piece of quantum interaction that occurs in the universe. Which means that if you are listening to me right now, if Everett's idea is true, then there's almost an incomprehensible amount of realities where you and I exist, but we've never met. This also means that everything that can happen does happen, which means that there exists a universe out there where I'm not giving this speech. There exists a universe out there that I'm giving a better speech or a speech on a different topic altogether. Okay? What does this mean? This means that quantum physics is no longer probabilistic. It's actually deterministic. Right? All outcomes just happen, but they happen in different branches. And this explains a lot of quantum phenomena. And this is the bedrock of quantum technologies. Okay? Hope you are following along so far, because we're going to go deeper. Okay, so now you want to go beyond the observable universe. You got to go fast, right? We have a very limited amount of time. So what you got to do, you start thinking, what happens, okay, if I travel at light speeds? Okay, now first and foremost, relativity tells us that this is impossible. Why? Particles that can travel at light speeds has to have a mass of 0. Okay, if you have mass, essentially you can't travel at light speeds. Why? Because the more and more you approach the speed of light, the harder and harder it becomes. Means you require more and more energy because you're getting heavier and heavier. So if you think of it, right, you want to go faster, you need more energy, but more energy makes you heavier, the whole E equals mc squared. So it's basically impossible to travel at light speeds. You need an infinite amount of energy for you to even approach light speed. Okay? So you're not allowed to go at light speed. The only particles that can travel at light speed is particles with no mass, photons, right? Particles of light. So they are going at light speed. So what does this mean? That essentially, these particles of light, they experience a time dilation, which is infinite. Basically, they don't experience time. They don't age. So if you're a photon, you would experience the entire universe in an instant. Imagine that, you experience the entire universe in an instant. But hey, there's no laws of physics that says we can't get pretty close to the speed of light. Okay? Yes. How do I go back? Right. Now, there's no laws of physics that says that you can't approach the speed of light. Okay? But what happens when you try to approach the speed of light? Well, firstly, there'll be a very strong time dilation. Later, I'll explain what time dilation is, okay? So everybody in the rocket would age much slower than those on Earth, okay? And time on Earth go much faster as compared to the people in the rocket. Does it make sense? Okay, can. Okay, so let's say you're 1 year on the rocket will be compared to about 7 to 8 years on Earth. That's crazy, right? So if you went for a long year trip and then come back, you certainly notice that everyone around you have aged. But there's another issue with traveling at light speeds, radiation. There's a lot of radiation in space. Earth, we're quite fortunate because we're protected from this radiation by Earth's atmosphere. In fact, actually not quite, right? In fact, airplane pilots have a higher risk of getting cancer because they're closer up to the atmosphere than they are compared to us on the ground. That's why they have a higher chance of getting atmosphere when you're at the edges of the Earth. So imagine, we are trying to travel at light speed beyond the observable universe. You're going to experience a lot of radiation. So if you don't have enough protection, you are going to experience a lot of damage to your rocket. Not only that, there's also random particles. There's also random particles in space. So imagine when you're traveling at such a high speed, at such a high velocity, and when you collide with any of these random particles, right, the impact will be huge and it can easily damage your rocket, right? But now, when you are traveling through space, right, even when you're trying to travel at such a high speed, there's something that you need to overcome. Gravity. But what is gravity? Have you ever wondered what is gravity? You probably heard phrases like gravitational attraction or the force of gravity, but at the same time, you might have heard that gravity is actually not a force. So what's gravity, right? Our understanding about gravity, our understanding of gravity that acts like a force actually comes from Isaac Newton. He was the one that created this theory of gravity that was very simple and elegant, right? I mean, you've probably learned this in secondary school, this formula. He basically said that gravity is a force which all objects experience in relation to one another. Or in other words, everything is attracting everything else. And the strength of this force depends on the distance between two objects. Specifically, it follows this inverse square law, right? So Newton's theory worked great for hundreds of years, right? And everybody was happy. And then came along Einstein with his description of gravity, which was called general relativity. Einstein said that gravity is not a force, but it is a geometric property of space-time. Or rather, it's a consequence of matter warping space-time around it. Okay, so what does this mean, right? So let's suppose you're on the equator of the Earth. Imagine Earth, right? And then you're walking in a straight line. From your point of view, you'll be walking in a straight line. But if you look at it from an outsider point of view, you can see clearly that you're walking in a curved direction. But is it your fault that you're walking in a curved direction? No, right? Because it's not your fault. It's because the surface that you're walking on is curved. And obviously, as a consequence of this, if you kept on going, right, you'd end at where you started. You just go one whole round, okay? So how is this relevant? Well, Einstein basically said that this is what gravity is. When something is orbiting something else, right, it's moving in a straight line. But however, due to the larger object, like this, right, I'm sure all of you have seen this video before. Due to the larger object, it bends space-time, it curves space-time, which is why it follows an orbit pattern, which is what you see, right, in our solar system. Einstein is basically saying that gravity is not a force. The medium that things travel on gets bent because some mass sits in it, right? You might have seen these diagrams, like I said, okay, when relating to general relativity, which looks a lot like trampolines, right? Just being bent. It's kind of a 2D analogy of what Einstein's gravity is. So yeah, so imagine you put a marble over here and then the marble starts curving in. So the thing is this, right? Let's compare Newton's theory and Einstein's theory. Newton's laws are both extremely good, are extremely good approximations and are extremely easy to use. The math is really simple. It's just GMM over R squared. Einstein's theories, right? Einstein's theory for general relativity. It's really hard. It's very complicated. So in day-to-day language as an approximation, you might hear physicists talk about the force of gravity, just because it's easier to think about it, right? It's easier to conceptualize. Einstein's general relativity is one of the most successful theories ever devised. And it has such vast implications like time dilation, black holes, the evolution of stars. The ideas are so deep and profound that physicists for over hundreds of years have dedicated their entire careers and lives to studying its concepts. Now, I've been talking about time travel a lot, and I'm talking about Einstein a lot, right? But have you wondered, while I was doing this, I was preparing for this speech, right? I was wondering, what if Einstein was wrong? What would you do if Einstein was wrong? And the answer is, if we found out tomorrow, okay, that somehow Einstein was wrong in a major way, right? Scientists would be thrilled. Imagine, right? Do you know how exciting that would be for the scientific, for the scientific world? Be a huge breakthrough. And this kind of thing only happens like once every 100 years to have a major scientific discovery. If we found out that gravity works in a different way, or if we found out that something could go faster than light, physicists will be jumping over each other. All right, they'll be trying to explain why, and they'll be trying to find out more. So in fact, right, I found out that 10 years ago, there was this experiment called the Opera experiment at CERN, and they published a paper that seems to suggest that neutrinos could travel faster than light. And eventually the experiment was botched, but between the period of publishing the paper and botching the experiments, there were literally thousands of papers being published, scientists being thrilled on trying to prove or disprove this theory, right? So if you can find an experiment that can break Einstein's theory, there's arguably a Nobel Prize for you, right, in it. And in another sense, in a very real way, we kind of know Einstein is wrong already. Why? Because Einstein's gravity doesn't work at the quantum scale. But until we have something else, his theories are some of the best that we have, okay? So now, I've been talking a lot about time, about traveling and the observable universe. But now, right, I want to look at time, okay? I mentioned time dilation. So we're going to go deep into time, okay? So looking at not only the physics of time, I'm also going to be looking at the philosophy of time. We realize that time goes so much deeper than one might expect. Why I say this? There's two ways to understand the word time, okay? There's physical time and subjective time. And the way we bridge the gap between the subjective time and the physical time is through the use of clocks. But even something as simple as the use of clocks, something as simple as building a clock, presents many fundamental issues, okay? So imagine you're building a clock for the very first time. Let's say you find some sort of regular beat, okay? Or phenomena that seems to have you find a regularly spaced rhythm, a regularly spaced beat, and you use this to measure your clock against. How do you know that this beat is regularly spaced? Well, you want to measure the distance between the beats, right? But in order to do that, you need a clock. So in order to build a clock, we need to have a clock. But wait, you might think, no, that's okay, right? We have physical constants like the speed of light that we can use to measure, right? Because speed of light is constant. But what do we use to measure speed? A clock. So how do you even build a clock in the first place? So clocks are very weird, right? When you start thinking about how to build a clock. So let's look at how to build a clock, okay? I have this theory. So let's say, right, we made a clock using every possible designs that ever existed. So I'm talking about sundials, water in a bucket, even an hourglass. What will happen? And even the atomic clocks, right? So for us, we use cesium, the cesium atom. I think it's about 9 million bits of a cesium atom represents a second, something like that. So we make all these clocks and we set them to the same time. So let's say 8 p.m. And we leave them overnight. And we come back 24 hours later. What do we realize? We realize that these clocks are no longer in phase. That perhaps the sundial will be 7:59. Maybe the cesium will be 8:01. They're no longer in phase. Maybe the grandfather clock might say it's 8:02. So the question is, how do you know which clock kept the time correctly? Which is the accurate one? And the answer is we don't. Okay, you're always comparing a clock with another clock. The way in which we decide which clock is right, not through an observation, but through an argument. And there's a lot of flaws in that. So the foundations of science aren't facts. They are arguments supported with evidence. Are you okay? Because we're going to go even deeper, right? So which is the most legit clock? Okay, so for us, right, for all like simplicity, the answer to that is we've been using this clock since 1967. So a second has been defined using a cesium-133 atomic clock. It's basically defined as 9 billion of quantum energy transitions that occur in this atom. So why do we trust that these 9 billion transitions are going to remain consistent? What happens if they fluctuate over time? But because we have the strongest argument, like I said, to believe that they won't change. And that is quantum physics, right? It's all about arguments. Quantum physics is, in a sense, our strongest scientific argument itself. There's scientific theory, and this is what allows us to understand things like radiation, helps us to build transistors, help us to build medical equipment that save lives. Our best clocks have been built around our best argument. And that's why we trust cesium atomic clocks more than any other clock right now, okay? So speaking about time, let's look at time travel. Yo, time travel. Age-old question, right? Since primary school, we've been looking at time travel. So now the real question is time travel possible? And the answer is, well, okay, there's two kinds of time travel, right? There's time travel to the future and time travel to the past. So let's talk about time travel to the future first. So we know this is possible, right? We are going to the future all the time. Literally, right now, we're going to the future. Somehow, the direction is forward. I'm not going to look at direction. That's a whole nother topic, okay? So we have a human being, right, that has somehow, and we have proven this, right? Because we have a human being that somehow managed to time travel to the future, right? Is this guy, Sergei Krikalev. He's an astronaut, and he has gone a whole 0.02 seconds into the future. It's quite little, but he went to the future nonetheless, okay? And this is compared to us on Earth, right? So the reason we know why he went into the future is that Einstein's relativity tells us that depending on your relative motion or the curvature of space-time, time will run at different rates in different places. And our astronaut friend here has spent over 800 days in space, going really, really fast around the Earth, which means that time has gone slow for him. The only thing stopping us from going really far into the future is that we can't reach light speeds yet. In fact, you need to go nearly 88% the speed of light just to slow down time by a factor of half. So time travel to the future is physically possible, okay? I'll talk about time dilation later on in a little bit, okay? But practically, it's very difficult. As what Michio Kaku has said, we have all the physics to explain time travel to the future is possible. We don't have, the only thing stopping us now is engineering. So let's talk about time travel to the past, right? So Einstein's theory of general relativity, which describes things like gravity, black holes, gravitational waves, wormholes. Again, like I said, these are some of the best theories that we have, right? He proposed a working time machine. What's it called? It's called a wormhole, which in principle seems like it could be done. Now you might be thinking, hey, there's a lot of paradoxes here, right? It should be logically impossible. Because if you can travel back to the past, like the grandfather theory, I can just go back, kill my grandfather, and then I won't exist. But do I exist, right? That's the theory, right? So what gives, right? So the really interesting thing about this is that physics might actually have an answer to a philosophical question. Very interesting, right? The caveat is this, right? That this time machine can only go back as far as the time machine was created. Okay, so if we made a time machine today, today is March 25th. Today is the furthest place back in time that you could travel back to. That means you couldn't travel back to yesterday because the machine didn't exist yet yesterday. So this will explain why we don't have time travelers from the future coming back to us, because we don't have a time machine now. Make sense? So things will need to unfold in a self-consistent way. Okay, so I'm not going to explain too much again, but in short, the theoretical model for time machine we have seems to solve a lot of paradoxes. Now looking at wormholes and how to build one, right? So wormholes was first predicted by a guy called Ludwig Flamm back in 1916. This is a few months after Einstein's theory was published. And we have over a century of thinking. So there's essentially two problems in wormholes, right? First is creating them and connecting two very vast distances in space together. And second is keeping them open. Because under forces, under gravity, wormholes tend to want to close. Okay, so you have to sort of like cut off point. You know, you have to have exposed edges of space-time. That's called a singularity in essence. And the only time that ever happens is in the core of a black hole. And you know that just seems to break physics and stuff like that. So we don't even want to talk about that, okay? But if we were to make a wormhole, we have a bigger issue with the second problem, keeping things open. So what scientists suggest is that we use this thing called exotic matter. So matter and antimatter, right? Matter is a positive nucleus surrounded by a negative electron. Antimatter will be opposite. It's negative nucleus surrounded by a positive electron called a positron. But antimatter will be different in the sense that matter and antimatter is positive in mass, is attractive under the forces of gravity. Exotic matter will be negative in mass. So under the forces of gravity, it will be repulsive in nature. So if you can imagine now, you put exotic matter inside, under the forces of gravity, you just pry the wormhole open. Okay? Again, I'm not going to go too deep into this. It's very abstract already. Moving on. Time dilation. So how does time dilation work, okay? Everyone okay, right? We're going to go even deeper. So Einstein's special relativity makes two key assertions. First is that the speed of light is always going to be measured to be same regardless of the frame of reference, right? So it's going to be same throughout. The second is called the principle of relativity, and it states that so long as two different points of view aren't accelerating compared to one another. It states that basically, right, the laws of physics are the same, right, regardless of where you're looking at. So this means a few things, right? As long as you're not accelerating or actively changing your velocity, you're allowed to think of yourself as stationary, right? So right now, let's say this example, I'm in this room standing here, and outside I see a plane. From my point of view, the plane is traveling around me. That's very fair, right? But from a passenger's point of view, they could think that I am traveling around the plane. You see, Einstein's theory of relativity gives no preference to the point of reference. But this is where things get interesting. So let's say, right, you somehow have a clock. And somehow you have a clock where, I don't have a whiteboard. Let's say you have a clock between two mirrors and you have light bouncing. So from your point of view, right, the light is bouncing up and down. And let's say I'm on a rocket cruising through space. And there's another rocket with another guy cruising through space, and they're coming towards each other, right? From my point of view, the light is going up and down. But when I look at the other rocket ship, their light is not going up and down. Their light is going like that. In triangles. Can you imagine? It's going in triangles. But we already say that the laws of physics are the same, and the speed of light is always constant. So when the distance of light goes from vertical up and down to diagonal, and when the speed of light is the same, that would seem to suggest that the person is experiencing a slower time than me. Right? It's only fair. But it's also fair to say that from his point of view, my time is going slower as compared to him. Very crazy, huh? Anyways, moving on. So this is basically time dilation explained in a nutshell. Okay. Now we're going to go even deeper. We're going to be looking at the metaphysics of time. Fuyo. Okay. So now we're going to the good stuff. Okay, this is the good stuff. So firstly, what is metaphysics, right? Metaphysics is kind of the academic branch of philosophy, which is kind of like a druggist kind of philosophy, but without the drugs, right? It's like a very stoner mindset. You are like asking questions like what is time? You're questioning existence, identity, stuff like that. So a lot of it tries to bridge our understanding between how we see the universe, the scientific context, and how we see in a subjective context. Now, the metaphysics of time is really interesting. Why? Because it says that, look, there are some things about the nature of time which don't seem to be covered by modern day physics. One of the key debates in metaphysics of time is the idea of whether there's a present moment or not. Is there a present moment? Obviously, all of us experience a sense of time passing, a sense of presentness. But Einstein's relativity time, Einstein's theory of relativity just states that time is just a fourth dimension. So there's no sense to time moving because it's just another dimension. You wouldn't say the x direction is moving, right? So interesting enough, right, there's three broad theories to this. These are actually what they're called, theory A, theory B, theory C. Like legit, they're called theory A, theory B, theory C. So people in theory A, right, believe that there's an objective present moment which moves continually forward, right? Something like entropy. So one version of this view is called the spotlight theory, which basically says, look, all the moments in time are equally real, but only some of them are available to us. Evidently, the ones that are available to us are called the present moment. So imagine you're under a spotlight, and the spotlight is moving with you. So people who believe in theory B disagree. They say that no, that's ridiculous. There's no such thing as the present moment. Doesn't make sense in physics. There's just a sequence of moments. However, they have a unique direction. Okay, time in a certain sense is kind of like a movie, right? So instead of you being under a spotlight, you're just on a movie reel where you can just go anywhere you want. Theory C is the interesting part. It says that there is no presence and then there's no inherent direction. Meaning time has no direction. So for instance, if you're someone from theory B, you will say that the Eiffel Tower was built after the pyramids. But if you're in theory C, you will say that the Eiffel Tower and the pyramids of Egypt were built in different times, but one was not before the other. That one we don't know, right? So this is going very, very deep, right? So this is raising a lot of interesting problems and interesting questions. You can go Google this if you're interested. I'm gonna stop here. Moving on. So we've been looking at time and space, but now I'm going to ask you, is science even real? Okay, is there even a scientific method? Answer is no. There is no scientific method. This was the position argued by Paul Feyerabend, right? He says that any law and order style attempts to boil science down to a certain set of methods which will only inhibit its progress. The only principle that doesn't inhibit progress is that anything goes. So this guy is a very outspoken epistemological anarchist. So he's once referred to as the worst enemy in science. He wasn't anti-science, okay? He was a trained physicist, but he strongly believed in the power where he didn't look at science as one big monolithic structure. He looked at science as a dogma, okay? He liked the view that sciences is a very different discipline, all interested in generating knowledge by using different methods and different approaches. But, I mean, you can see why he earned his reputation, right? Because he said things like neither science nor rationality are universal methods of excellence. They're just traditions. So he said that science is neither a single tradition nor the best tradition there is. He argued the idea that science was free. He argued that there was biases in science, that the values in science are all wrong if you look at history. Science has been greatly informed. It has been greatly influenced by culture, by heritage. Right? This was his main argument. And he said that we have an obligation to recognize this. We have an obligation to recognize this and think about science a little bit more carefully. Because if we consider things like religion, culture, tradition, heritage, it's just gonna hold back progress for science. So that's why he argued for the principle of anything goes, right? This theory of anything goes is used to advance our scientific knowledge and thinking. And it's on, right? So, yes, he uses examples from Copernicus and Galileo. So where these people, right, had to disregard their intuitions around how motions work. Okay, so before, right, people used to believe that the sun and the planets orbited around Earth. Galileo thought that that was wrong, right? That we orbited around the sun. But it was very counterintuitive because if you think of it from his perspective, if you drop a ball and the Earth is moving away from you, wouldn't you expect the ball to land in a different position? But no, you realize the ball lands in the same position. So it's very counterintuitive, right, to the idea that Earth is the one that's revolving and not stationary. But Galileo had to go against that his own intuitive, and that's what led to the progress of science. So basically, this is what the guy is saying, that science should be independent of culture, of heritage, of biases. Things like gender bias, sexual bias, it is present in science a lot. Now, I think he made some really important points, and many philosophers agree that there is no single scientific method. So in chemistry, you can test the reaction again and again and again, as many times as you want, as long as you have the materials. But with astronomy, right, you can't exactly ask the supernova to explode one more time. So whether total anarchy is the answer remains to be seen, but you can understand why he was a controversial figure. As you might expect, not many scientists are a fan of him. Perhaps science is better characterized as a process of becoming less wrong over time. We're getting closer and closer to the truth. In order to buy the argument, we need to believe that there is an objective reality, that there is an objective truth. And that's a view called realism. So now we need to be careful when we use the word science. Don't get me wrong, it's a very great word, okay, but it can mean two very different things. It can mean science as in the organized body of knowledge that we've created, or science as in the thing that scientists do in order to create their knowledge. That's the whole scientific inquiry. Most of the times in education, when we are teaching science, we're teaching the products of scientific thinking. We're teaching our students formulas. So here's what we learned so far, here's what we know. But this is all great fun, useful, necessary, but we tend to we tend to de-emphasize science as a process. Science as a means of investigation. Science as a reason for argument, of collaborating with others, trying to work out the truth, of realizing that we're on the same team. We're trying to solve the problems. We're trying to solve the same problems because right now in society, we don't have a knowledge problem. We have an understanding problem. Scientific literacy and trust doesn't come from telling people facts from authority. It comes from reason and argument, helping them to understand why we think what we think. So the word science comes from the Latin word scientia, which means knowledge or expert or science was used to describe what we call science today. It used to be given the common label called natural philosophy, which is old school and as archaic as it is. I kind of like this phrase as a description for the process of creating knowledge or creating scientific knowledge, because we invent common knowledge by asking questions, investigating them, testing theories, and then ultimately arguing with other people to come to a consensus. So speaking of understanding, right, let me explain a problem to you that's in the root of all science. Going even deeper, right? Most philosophers consider this unsolved and believe that perhaps it will never be solved. It's called the problem of induction. There are many kinds of reasoning, right? The two main ones are deductive reasoning and inductive reasoning. Deductive reasoning is associated with like the whole Sherlock Holmes kind of thing. We like deductive reasoning because the conclusion always has to follow if the premises are true. So here's an example. All men are mortal. Socrates was a man, therefore Socrates is mortal. Basic hard logic works every time. Right. But inductive reasoning, however, is a bit weaker. Example would be this. Every time I meet Tawaku, he's nice. Therefore, Taoku will always be nice. Right? That's an inductive way of reasoning, and that's very weak. It usually follows that if B follows A every time, B as a law has to follow A, which is not true. From our own personal reasoning, from our own personal experience, we know it's not true. Inductive reasoning doesn't guarantee its conclusions. Just because you see a pattern doesn't mean it's going to be repeated forever, right? So the problem is that all our scientific knowledge, all our laws of nature seem to be based on inductive reasoning. Our laws of gravity, electromagnetism, light, are all formed from patterns that we've seen previously. But they all rely on the assumption that the pattern is going to continue. You might be thinking, no, these are laws and they're different from pattern. But how do we know that we haven't seen these laws in a law? How do we know these laws are true? We've never seen these laws in a law book, right? How do we know that these laws be consistent outside of our own observable universe? We don't even know what lies beyond that. We just invented them to explain the evidence that we have so far. And if the history of science has taught us anything, a new discovery can cause us to rewrite the textbooks about everything at any time. This idea really starts to mess with you. If you start to think about, if you start thinking about it, because humans very naturally use inductive reasoning. Think about the way you learned not to touch a hot pan, or trip over, or walk over a slippery floor. You experience a negative, you had a negative experience, and you associated the outcome to the experience. And then when you use that pattern to make a judgment not to repeat it again, right? So we do most things because when we do something, right, it's because we have a positive experience. And we expect that this positive experience will repeat. Human instincts is fundamentally inductive, and inductive logic doesn't guarantee the outcome. So if induction is at the heart of all science, how can we have faith that science is going to work tomorrow? Most scientists and philosophers, when they hear this problem, they despair a little bit. They say that you have to assume on some level that the universe is going to hold certain patterns, that the past in some way will resemble the future. But that was okay. So, oops, let me go back. Speaking of all this, right? Here's an uncomfortable idea. Science can't actually prove theories. It can only hope to disprove them. Okay. This might sound a bit ridiculous, because we hear things like scientifically proven theories but here's an example. Suppose you are trying to prove the claim that all swans are white. What do you have to do? You have to find every single swan that ever existed in all space-time, and you have to confirm that it's white. But to disprove it, you just have to find a swan that's not white. So you realize that it's easier to disprove than to prove. So this is something that was observed by this philosopher called Karl Popper. He said that there's an epistemic symmetry, there's an epistemic asymmetry between proof and disproof, right? So we can't prove our laws of physics hold true for every time and place in the universe, because we don't have access to every time or place in the universe. We can't check that every electron is the same. We can't check that every nuclear reaction in a nuclear plant is the same. We can't check that every reaction in a star is the same. Popper argued that basically the way we should decide a scientific belief is through a sort of survival of the fittest, right? It's like the selection, natural selection, something like that, right? What we do is we run our current theories, and whichever theories don't prove, or rather goes against experimental results, we throw them away. The logical theory would be the one that seems to prove the experiments. So there's no certainty in science. And while yes, it does seem to be the case that the universe is written in the language of mathematics, right? There's certainly been the case that everything that we see is based on inductive reasoning. Everything in science, in essence, is flawed, if you think about it. That when we say F equals to ma, you have no way of proving to me that you'll be the same tomorrow, that F equals to ma, and perhaps not F equals ma squared. But I think realizing this and coming to terms with it it's really quite cool because amidst all this uncertainty, right, we have clearly made progress in how we understand and operate within the universe from the ground layers of philosophy to the modern day experimental process. So how does this link to all of us? I'm at the last part now. When you look up into the night sky and when you observe the stars, and you ponder, you awe away at the greatness of what you see up there, you realize that it's really not a passive process. When you look at something, it's a very active process. Why do I say that? When you look at something, you're interacting with that thing. What does it mean to see? To see is an active process. Light has to bounce on the object, and that light has to enter your eyes. So when you see something, you are directly interacting with the object. When you look at stars, you are interacting with the stars. Observation is never passive. Okay? So before I end, right, I like to play this video by Neil deGrasse Tyson. Julia, if you don't mind, like a 3-minute video.
What is the most astounding fact you can share with us about the universe?
The most astounding fact
The most astounding fact.
is the knowledge that the atoms that comprise life on Earth, the atoms that make up the human body, are traceable to the crucibles that cooked light elements into heavy elements in their core under extreme temperatures and pressures. These stars, the high mass ones among them, went unstable in their later years. They collapsed and then exploded, scattering their enriched guts across the galaxy. Guts made of carbon, nitrogen, oxygen, and all the fundamental ingredients of life itself. These ingredients become part of gas clouds that condense, collapse, form the next generation of solar systems, stars with orbiting planets. And those planets now have the ingredients for life itself. So that when I look up at the night sky, and I know that, yes, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us. When I reflect on that fact, I look up. Many people feel small because they're small and the universe is big, but I feel big because my atoms came from those stars. There's a level of connectivity. That's really what you want in life. You want to feel connected. You want to feel relevant. You want to feel like you're a participant in the goings-on of activities and events around you. That's precisely what we are, just by being alive.
So, every atom in your body came from a star that exploded. We are all just a collection of stardust, right? And I say this in the most highest exalted way. The fact that we humans, who ourselves are mere collections of fundamental particles, have been able to come this close to understanding the laws governing nature in our universe. That's quite a great triumph for mankind. So as I speak, during my speech, I mentioned things like, is time real? Is science real? you may feel small, but I hope that from this speech, it kind of makes you think about the status quo, about how our current scientific processes can be improved, right? We have achieved the earth-shaking, the breathtaking, the groundbreaking. And what we hope to do now is leave a mark in the heavens. And remember that this journey, right, through the universe isn't just about flags or footprints. This is about sustainable science and feeding forward the advance of the human spirit. Because remember to always share this enthusiasm with those around you. And later, when you look up at the stars, do think about all the things that I've said. Whether this is real, whether time is real, and why is time the way it is? And why do we believe things that we do? Don't just look at the stars for what it is, but also think about what they represent and what they mean, and how we are connected to these objects. Turn towards the night sky as a conclusion, and not as a conclusion, but as a preparation. And what our great Stephen Hawking has said, don't look down your feet, but look up at the stars. Thank you very much. If you all have any questions, I don't know what questions you all have. It was a very philosophical journey, but no questions. Okay, boss. Thanks everyone.